Thank you. So thank you also for coming here. I'm going to talk about, as I said, loop optimization. So this is a disclaimer that I received DOE funding for this research. And as the title implies, I'm going to talk about first about the good thing, which is the things we already have, which are good in LLVM. Bad things that are not so good, but not that problematic. You can like improve the source code. And the ugly stuff that I think needs to, makes us need to rethink loop optimization. But first to go into why we do loop transformation in the compiler. So in the past, I had some discussion with other people say, no, don't do loop optimization in compiler. This should take place in another level. For instance, it should be in a library, so you're not dependent on a specific compiler. That's an approach like tensor comprehensions or Halide does. Or you do invent a new language specific for your problem, so you have domain knowledge in that program and could potentially optimize more. So when doing in the compiler, you have the advantage once that you can add this parameter, and it saves you to apply this this loop transformation manually in the source code. So this saves you from repeating this statement code multiple times. Another possibility is you don't even need parameters to do the compiler. You have heuristics, which tells the compiler when it is a good idea to apply a specific optimization. Or another motivation we have, you want to do loop auto-tuning and tell the compiler, try out another loop. So there's this project ATJIT, there was a lightning talk yesterday that tries out loop optimization to find out the best one while the program is running using a JIT compiler. So loop optimization are already all around. So about every single optimizing compiler supports some kind of loop transformation, and most of them export them as some kind of parameter. So coming to things that I think get good in the compiler, we actually have a couple of loop transformations which range from loop unrolling and jamming, loop idiom detection, vectorization, loop distribution, and these are modular. We can switch them on, off, and independently. There is no necessary interaction between them. We also support controlling some of them using parameters. So in this case, we had unrolling, vectorization, interleaving, and loop distribution that can be controlled from the source code by the programmer. And we have a loop canonical form, which consists of a pre-header, a header, an exiting blocks, and a latch, which has a back edge back to the header, which loop transformation can rely on, that this exists. And if they want it, there's also loop closed SSA form that might simplify some loop transformations. We also have shared for all the loop transformation a couple of infrastructures. So every loop transformation can use make of the loop info, which is kind of a precondition to actually know the loops which are to optimize. Scala evolution and the predicate Scala evolution are pretty good for the things that they are doing. Well, that was unexpected laughing. I'm not sure whether that related to Scala evolution. Okay, next thing, we have like preparation passes, like loop rotation, loop simplification to improve the canonical loop form that we have. And for transformation, multiple passes make use of the loop versioning class, which copies your loop. So you can modify one and then have a fallback in case you have some conditions which fail in the case these are necessary for your transformations. So we had like 4 slides about what's good. So next thing is bad. I may see a couple more slides. First of all, to understand what's going to is to understand what's the structure inside clang and LLVM is, which is shown here. Probably most of you already know this, but we have like the in clang, the IR generation goes to IAM, passes a couple of passes. Some of them are loop transformation passes, which are then passed on the backend. So I told you we have a couple of loop transformation, but actually some of them are just disabled by default. and has like internal switches to make them enable. The probable reason they are not as mature as they could be, so they are, might miscompile your code or not give the speed up you're expecting it to have. We also have a static loop pipeline. So I give the examples with the pragmas. If you want to have a specific order of the pragma, for instance, if you want first interchange and then distribute, we cannot do that because the loop interchange, if activated, would takes place before loop distribution. So this is something we cannot realize in the current parser alignment. A similar problem is with the clang IR generator. If you want to have something parallelized, it's outlined very early, just in the process of generating LLVM. And if you do a pragma unroll at the same time, either before or after, doesn't matter. The pragma unroll directive is just dropped. It does not appear in the generated LLVM. As I said, the order actually is important. So in this case, we have an unroll and then reverse in two different orders, and we yields different code for this time. This is something we do not really support. So the metadata which we have in the LLVM MIR to direct which transformation to execute is unordered by design. And at the moment, I have a patch under review trying to fix this. Next to the order of the just loop passes in between, we have also other passes in between. And sometimes they struggle with preserving the loop canonical form. So I have cases where simplified GFD or jump threading would destroy this loop canonical form, so it would be not detected as a proper loop afterwards. It's also a problem that these non-loop passes needs to preserve some of the passes in between. So, for instance, loop info or Scala evolution, or just thrown away. There are some of these non-loop passes which make loop transformations more difficult. So it's the loop invariant code motion and global number value numbering. And for some loop transformation, also the loop cloud SSA. Here's an example. In the top, we have two loops which we can transform into each other using a loop interchange. But once we apply loop invariant code motion on the left one, or load partial redundancy elimination on the right one, this is a one-way street. There's no path reversing it. We are stuck with this transformation, and we can't do a loop interchange anymore after that. This loop transformation also have kind of a lot of infrastructure that are specific to this path. So we have a lot of dependency analysis. Each of the passes do their own profitability analysis, so independent, and often also the code transformation. In the case of loop closed SSA form, might be good if you do only innermost transformations, but if you do want to have outer loop transformation or something else, it adds additional artificial dependencies between the instruction, making your transformation more difficult. There's also the loop rotated form is also sometimes an obstacle. In this case, we could express the top code just as a single for loop, and it's transformed by the loop rotation into the bottom one. If we have an outer loop, we have suddenly this additional if condition in between, which made problematic. For instance, if you want to do loop interchange, want to interchange the outer loop and the inner loop, and suddenly there's the if condition in between. Does the if condition matter? Is this a sleep rotated form? It does not make the transformation easier, unfortunately. There's also a lot of boilerplate. So the loop transformation passes are quite big, which includes boilerplate code for two pass managers. They have to when they're doing their thing, they have to repair the control flow, so restore this loop structure, if possibly restoring the loop closed SSA form. The SSA form needs to be restored anyway, and care for the preservation of passes. For instance, it is obligated to preserve loop info, since this is necessary as if they are loop passes. To illustrate that it's not necessarily needed in all the cases, here is what we can be done in Poly. Poly uses so-called schedule trees, which is a hierarchical presentation of loops. In this case, to do the loop distribution, it just has to switch the order of this so-called band and the sequence node. Then it generates the code from it and the code generation pass, and you have effectively implemented your loop distribution. This is actually the code for it. It's even more than necessary, since the legality check could be put out of this this function. It's not quite a fair comparison, because you also need something that calls this this function, and you need some boilerplate as well. I think it's kind of an impressive example how easily you could do powerful transformation with just a few lines of code. There are some smaller issues as well, that the induction variable is already promoted to 64 bits, even if it's not necessary. So the next two things are things that are ugly, that's more difficult to handle than just fixing something in the current pipeline. One thing is the profitability. So at the moment, the loop passes consider themselves what's profitable, and they are, but sometimes, or I would say even in the majority of cases, you need a combination of loop passes, loop transformations to do your to get the optimal performance. Once this loop distribution pass needs to know would be a distributed loop out of your main loop be vectorizable or not if not, there's no point of distributing it out of the main loop. In the current hierarchy, there's something strange with a loop unroll and unroll-and-jam. So unroll-and-jam does not want to be applied if there's a proper unroll in front, or the unroll is forced. But it's scheduled before a loop unroll in the pipeline. So to avoid that, it asks the loop unroll functions to would it be in forced unroll. If no, if yes, then it would not unroll-and-jam and leave it to the unroll pass afterwards. So this is kind of a interaction between passes, which makes it more difficult to understand. And then there's an issue with the loop versioning. So I told you about this loop versioning class, which duplicates the code used by 4 different loop passes in LLVM. And if every one of those would do the loop versioning and get an exponential number of copies of your code. So for illustration, you start with a single loop nest of 2 loops. You do optimization of one of them, which introduces a runtime check and a fallback version. You do another transformation, for instance, strip mine, which introduces another intermediate loop. So we have 2 loops, you get 5 out of it. We apply another transformation, and now it's getting so small you can't read it anymore. And with the 4th one, I don't bother about it. So, but that's the point of the talk, is to propose something. So because of this, I'm proposing something to improve something, which is actually having not a sequence of passes, but a single integrated loop pass, which cares for all of it, which has some control in what analysis one can preserve this analysis, and there's no non-loop pass in between. So you can apply then the optimization like this. You get from more specific things to more general ones. So very specific is if you have you detected a matrix multiplication and instead call a BLAS library. The unroll-and-jam can just check, okay, if we can unroll-and-jam, then do it, otherwise do an unroll. So the difficulty we had before with the loop unroll-and-jam and loop unroll. If there is a parameter inside, we actually skip all of that and just apply the parameter, since the user seems to know what loop transformation there is to do. For a backing infrastructure, I suggested before on the mailing list, okay, using the LLVM IR, but the responses I got was more, no, don't misuse the LLVM IR, so I suggest an alternative to what I call a loop structure DAG. Here's an example. So if your representation of a function as a hierarchy, you have loop nodes in there, you're here in blue, statement nodes which have side effects, and expression nodes which are floating nodes tied to a specific location where they are evaluated. So this not coincidentally resembles somewhat the schedule trees we had before. You can also do like a simple copy. If you do a copy, for instance, we in this case we modified the the K loop, and we can reuse most of the node from the original function. So we don't need to clone the entire function. So we can have multiple variants at the same time, kind as vplan. It's a special thing. So there's this assumption that s is not the minimum integer. Otherwise, you would get an endless loop. This is an assumption that the code generator at the end would consider add as a runtime condition to decide when to go to the fallback version. But there's just one fallback generation generated. We don't have an exponential blow up. There's also a special thing to support this. So you've seen the nodes we have only go to the children. So we don't know what is a parent. And here's an idea that I stole from the C# compiler, which they use to track syntax. So if you edit your document, they do not need to throw away the entire tree, but just parts of this tree and keep the most of the data intact. So this is a bit how it works. You have a root node, you have your green tree with just nodes down, and you have a red tree, which points to the parent. So now if you do a change, you invalidate this node and want to create a new tree, you get a new root out of it, and then you generate the red tree, but only the nodes you're interested in. So these are generated on the fly, and if you don't look into the other nodes, you don't need to expand them. But if you do, you are creating the full red tree. In addition to that one, we have, I'd suggest to have a component system. So we have like our integrated loop path and some puzzle pieces that are missing. For instance, to get closed form expression, we could either Scala evolution or predicated Scala evolution, which might add additional assumptions to that one, which are enabled at a higher optimization level. And if you go higher in the optimization level, you can do something more sophisticated, for instance, do a polyhedral value analysis, which could be more powerful. Another piece is missing in the access analysis. So if you have an array index substrate to determine which element it is accessing in the array, so you have one-dimensional and two-dimensional ones. You have a dependency analysis from something very simple, control flow intuitive, something Scef-based, something we currently use, or somewhat reuse something the other loop passes already use, or go to full-fledged polyhedral dependency analysis, so like about the most exact you can get, and choose what kind of linear program solver you want to have depending on what optimization level you have. The dependency analysis, there is the SSA dependency are expressed as register dependencies, which can be expanded to array in case it needs to by the code generator. So this removes restrictions on what you can modify. Also propose something like predicated preferred non-cyclic control flow. If you do it, have non-cyclic control flow like in the CUG inside this loop nodes, look like something like this. But if you want to modify it, it's more difficult. Instead, you can just have the statements as a sequence of statements and model these the control flow using control dependencies. You can do this, for instance, to reorder your statements in between. In this case, I can split in here, do a loop distribution, one part at the top, one part at the bottom. Now imagine you had to modify the control flow we had at the beginning. At the end, we would do some code generation, either to LLVM IR, or if you want to vectorize to vplan, since I do not want to duplicate the vectorization infrastructure we already have. So the pipeline would be in general like this: create the loop structure, do some canonicalization on it, the analysis I presented before, do some transformations, one of them, and then since we could generate multiple alternatives of the same tree, and then have a cost model which chooses where the tree which it thinks is the fastest, and then do the code generation at the end. So that's it for me. I want to thank you for attention. So one note. So there's another talk about from Kit Barton, who implemented loop fusion using the old methods and the difficulties he had with it. And then I would like to ask, I presented lots of DIA, nothing has really been implemented here. So who in the audience thinks it's a good idea to have an integrated path? Okay, who thinks we should do something else? For instance, keep the current loop structure. Okay, who pays attention and noticed the green bar at the bottom? Thank you. So then, waiting for your questions.
Yep, thanks, Michael. Anybody have any questions? Raise your hand or bring you the mic. There's we go.
Thank you for the talk. Did you think about merging vplan, the vectorization analysis, with what you are doing in loop?
Yeah, I think the goals of vplan and what I am proposing are different. So vplan intends to keep the loop structure, even if it's possible to modeling them. But you have to do modification of that. Then you have to a lot of interactions, like dependency between the different loop hierarchies and so on. And if you want to do loop distribution, you need to tear them apart and join them again, which is this lower level stuff which I mentioned before. Whereas I try to do to simplify, just having a loop transformation, a tree transformation to do your transformation, and everything else is cared for you. It's also the idea of having multiple, to have the cheap copy of your entire loop hierarchy, so you can have multi-versions compared to them. vplan has also this, but that you create entire copies of the entire vplan at the moment.
Okay, any other questions? There's one.
Thank you for the talk. So the DAG that you're proposing, so it will, like every single node will be like self-sufficient expression of the corresponding IR instruction that it was built from, or it will just point to the IR that it came from?
So it's in principle independent from the IR, so no pointing to them, but from the original tree, you have constructed from EVR has a link to the original IR it represents. This is for in your code generation to detect, okay, this thing has not been modified, I don't need to generate anything, I use the old code I had before.
Okay, so the building of the IR resulting from the DAG, when you finish like optimizing loops and you want to rebuild your IR, you will just use like the original instructions, or I'm wondering about the cost of the building DAG and building IR out of the DAG.
So if once you modified it, it would be independent from the IR. Just if you did not modify it, so I always intend to represent the entire function tree. And the stuff you did not touch as well because you did not find any optimization opportunities, it would stay as it is. The things you changed, the loop distribution would be generated from scratch without considering the old IR.
Okay, thank you.
Okay, that's all the time we have. So if you have more questions, you can talk to Michael up here, find him a little bit later. Thank you very much. We'll start with Jim Lin in a little while.